Hello and welcome to my presentation on question 4, which was about kinetic and gas theory. We will look at ideal gas law and van der Waals gas law, and I can only hope that I got, right answers and that hopefully I can help with anyone who maybe didn't understand it or just wanted a little bit of help. But yeah, so here we go. There's three parts to the question, but there's two parts in the first part of the question. It gets a bit complicated, so I'm just going to do it step by step to not overcomplicate anything. So we'll look at this, and it says a sample of 255 grams of neon gas occupies 3 decimeters cubed of 122 Kelvin. Using the ideal gas law, calculate the pressure of the gas. Now, we're going to ignore this bit for a sec, just so we can focus on the ideal gas law. And if we're looking at it as an ideal gas law, like it says in the question, we've got to look at Avogadro's hypothesis, which says that the volume of any gas proportional to the number of moles at any given temperature and pressure. Now that gives us this lovely little equation here, which is easy to understand. PV equals nRT, I'll go through in a sec. But let's look at a couple of laws just so we can it makes us understand the question a bit more and understand the second part a bit more, which is gas particles have no volume and gas particles do not attract. Now, this bit will come in handy, or these bits will come in handy on the second part of the question, but for now, let's just stick to working out this equation. Now, pressure. We have atmospheres, torrs, pascals, bars, and they can all be worked out from each other in the question. We haven't been given the pressure yet because obviously we need to work it out. So we'll look at the rest of the equation. We've got, if you look in the question, we've got 3 decimeter cubed, and that's one of the measurements. We can either have it in meters squared or meters cubed or decimeter cubed, sorry. We've got a number of moles, you should be able to work that out. The constant, which I'll go through in a minute now, and then temperature, which is 273, which is 0 degrees in Kelvin, then plus wherever the degrees is. But we don't need to work anything out like that because the question is already given it to us in Kelvin. Now, if we look at the constant, we can see that it is in decimeter cubed. Now, the reason that's important because we have it in pascals and meters squared, and then we have these equations. Then we have in atmospheres and decimeter cubed, and torr and decimeter cubed. Sorry, I think I said meters squared. It's meant to be meters cubed, as you can see, but sorry, it just slipped up. So yeah, so it's in so we have the choice between it in atmospheres and the option or having it in torrs. Now, I decided to go with atmospheres just because I thought it was easier and I'm used to using this constant in different stuff anyway. So I thought, yeah, I'll just stick to that, stick to what you know, and unless the question is asking different, I would suggest using that just because you will come across this constant a bit in other work. So yeah, that's my suggestion. Now we can actually look at the question. So we know the temperature, we know the constant because we just talked about on the other slide. Then we will look at the number of moles, which is obviously how you worked. You should know how to work that out by now, which is the mass over the molar mass. Then we have the volume, which is 3. Shove it all in the equation, a bit of rearranging, and we get this number. And this is 42.19 atmosphere. But the second part of the question is asking about it being a van der Waals gas. So if we get rid of all of this, we can now look at it as a van der Waals gas. There you go. So this is what you would do if you're looking at it as a van der Waals gas. As I said in the previous slide about some of the laws, unlike the ideal gas law, it does attract only slightly. So that means it deviates from certain patterns and that increases the pressure. It also does, the gas, it does have mass. So that obviously affects where it can go and where it can go in the container and at what times. So we've got the two formulas here to work out the actual volume and the actual pressure of the gas, which is the volume of the original, take away N times B. Now, B and A, they depend on the element or the molecule that you're using, but it's often either given to you in a question or a data sheet or whatever, but it will be given to you, so that's something you don't have to work out. So we just plonk all that into a calculation and we get this in atmospheres. Shouldn't be in atmospheres, but for some reason, maybe the PowerPoint messed up or something, but it shouldn't be in atmospheres, but oh well, you know it shouldn't. And that it should be in decimeters, but it doesn't matter. It doesn't matter. What's important is that we've worked out the actual volume. Now, once we've worked that out, we can put that into the formula to work out actual pressure, which is 42.19 plus the number of moles divide the actual volume squared and times A, which is also given to us in the question. And as we can see from the question, 46.39 atmospheres. And if you go back, we can see that the pressure on the ideal gas law is smaller, and that is because of this attraction, this deviation from the pattern, and the fact that it has mass. So it means obviously I can't go in certain places. I have explained this before. Don't want to sound like a broken record, but yeah, let's just move on to the second part of the question, which is 40 grams of helium gas is then added to the neon gas in the container without changing temperature or pressure, and assuming the ideal gas law behavior, assuming that the ideal gas behavior is in the ideal gas law is active in both gases, calculate the vapor pressure of helium in the system. Now, we use the same formula, and that's because it's an ideal gas law, so that means it doesn't attract. So we can just put it all into the formula and we get this, which is the 3.37 atmosphere, and that is because it doesn't react. This is quite simple, similar to the other question, but we don't have to do anything with van der Waals gases. Now, the third part of the question is asking us to sketch the Maxwell-Boltzmann distribution and then work out the roots mean squared speed for each. Now, this is the Maxwell-Boltzmann distribution for, the Maxwell-Boltzmann distribution for both. As you can see, the neon is flatter than the helium, and that is because of the fact the neon is heavier, both physically and with the MR, because obviously the MR is 20 and the mass is 255, so obviously it's going to be flatter. And with the helium, same thing, with because it's lighter, so it will reach higher peaks. Now, I thought I would put down the different formulas to work out different parts of the Maxwell distribution. We have the max, which is the highest peak. We have the average, which will never be on the max or the average because it is not equal on either side. It is not an even shape, so obviously it won't be equal. If you look at the max, it's not equal on each side. Same thing with the neon. So the average will be somewhere obviously in the middle. Then we would have the root mean squared, which is by there, as you can see with the black arrows. Now, to work it out, I've written all the formulas by here, but we only need the root mean squared, which is this one by here. So let's look at that more in depth. So I've worked it out for neon and helium. So we've put in the decimeter cubed, we've put in the constant, we've put in the temperature, and we have put in the MR. So we just put all this in. The 3 was, if you look here, the 3 is already there. The constant, and then we have the temperature, and then the MR, and then we get this number for the neon. And then we get, obviously we do the same thing with the helium, and we get 2.74. And that's it. That's the entire question. Hopefully everyone understood that. If there's any questions, let me know, and hopefully, yeah, this helped.